device that creates a powerful magnetic field to trap and stabilize plasma. Once operational, ITER is expected to produce 10 times the energy it consumes during fusion reactions. This would be a game-changing milestone in the quest for fusion power. ITER is currently under construction, with its first plasma expected by the early 2030s. Meanwhile, private companies and startups are also entering the fusion race. Firms like Commonwealth Fusion Systems, Helion Energy, and TAE Technologies are building compact and innovative reactors. These companies often employ cutting-edge materials and artificial intelligence to optimize plasma behavior.
Some are using alternative fuel cycles and novel confinement geometries. Their goal is not only to achieve fusion but to commercialize it within a practical time frame. Helion Energy, for instance, aims to deliver electricity to the grid using fusion as early as the late 2020s.
This new wave of fusion entrepreneurship is bringing fresh energy and investment into the field. Venture capitalists and governments alike are recognizing the transformative potential of fusion energy. Hundreds of millions of dollars are being poured into research and development. The promise is simply too big to ignore. Fusion could provide energy security without the environmental and geopolitical costs of fossil fuels. It could power cities, industries, and even space missions with minimal ecological footprint. It represents not just a technological leap, but a civilizational one. However, significant challenges remain on the road to fusion power.
Sustaining a stable fusion reaction over long periods is still not routine. Maintaining plasma stability and avoiding disruptions inside reactors is an ongoing hurdle. Advanced control systems and real-time diagnostics are required to prevent catastrophic plasma collapse. The materials used in reactors must also withstand extreme heat, radiation, and neutron bombardment. Even the most advanced alloys struggle to survive for extended periods inside a working fusion environment. This raises serious concerns about reactor longevity and maintenance costs.
Furthermore, producing the fuel for fusion, typically deuterium and tritium, is complex. While deuterium is abundant in seawater, tritium is rare and must be bred inside the reactor using lithium blankets. This adds an extra layer of engineering difficulty. Then there are the economic concerns.
Fusion reactors are expensive to build, with costs running into tens of billions of dollars. They require precision engineering, ultra-high vacuum systems, and massive magnets cooled by superconductors. Scaling down costs for commercial viability will be one of the defining challenges of the next decade.
Despite this, momentum is growing due to increasing global urgency for clean energy solutions. Climate change and energy insecurity are pushing governments to invest more heavily in breakthrough energy technologies. Fusion is no longer seen as a distant dream but a necessity for a sustainable future. The Paris Agreement and net zero pledges are impossible to meet without radical transformation in the energy sector. Fusion could be a central pillar in that transformation. Moreover, fusion power is inherently safe. There's no risk of runaway chain reactions as in fission reactors. In the event of a malfunction, the reaction simply stops. This safety profile makes fusion an attractive alternative to both fossil fuels and conventional nuclear power. The growing alignment of science, policy, and capital is accelerating fusion development. Collaborative projects like ITER show what can be achieved when the world works together. Global scientific collaboration has created a foundation for rapid innovation and shared knowledge. China, South Korea, the EU, the US, and others are contributing talent and resources to this global mission. The dream of fusion power has become a collective human goal rather than a national one. Academic institutions are also playing a vital role. Universities are training a new generation of plasma physicists and fusion engineers. They are pushing the boundaries of simulation, materials science, and control systems. Open-source data sharing and cross-disciplinary partnerships are increasing the speed of innovation. Meanwhile, international conferences on fusion are drawing record numbers of attendees. This enthusiasm reflects a growing belief that fusion is finally within reach. Another exciting area is the development of alternative reactor concepts. Stellarators, spheromax, and compact toroids are being explored as potential alternatives to tokamaks. Each design comes with unique advantages and challenges.
Stellarators, for instance, offer improved plasma stability but are difficult to construct due to their complex shapes. Spheromax are more compact and may allow for cheaper reactors, but plasma control is harder. Researchers are running simulations and small-scale experiments to compare.
Performance metrics. Machine learning is being used to optimize reactor configurations and forecast plasma behavior. The fusion field is evolving at a pace never seen before. The progress made over the last 5 years exceeds that of the previous 3 decades. Breakthroughs in superconducting magnets, high-power lasers, and real-time plasma control systems have redefined what's possible. Advances in materials like tungsten and silicon carbide are pushing durability limits. Even the design of reactor walls and diverters is becoming more sophisticated. These improvements are paving the way for longer and more efficient fusion runs. The scientific community is cautiously optimistic. There's growing consensus that a demonstration fusion power plant could be operational within the next 10 to 15 years. If successful, such a plant could serve as a blueprint for global deployment. It could reshape geopolitics by reducing dependence on oil-rich nations. Fusion energy could become the backbone of a resilient, clean, and decentralized energy infrastructure. The economic implications would be enormous. Jobs would be created in engineering, manufacturing, and operations. Regions rich in raw materials like lithium could experience an economic boom. Fusion could lift entire nations out of energy poverty.
This is particularly important for the Global South, where energy access remains limited. Fusion could empower these regions to leapfrog outdated fossil fuel systems. It could power desalination plants, electric vehicles, and smart grids. Fusion energy may also unlock the next era of space exploration. NASA and private space companies are eyeing fusion as a propulsion source. A fusion-powered spacecraft could reach Mars in a fraction of the time it takes today. The technology could revolutionize deep space travel and exploration. It could also power off-world colonies with clean, reliable energy. Fusion is not just about electricity, it's about reshaping the future of civilization. This technology stands at the intersection of physics, engineering, and global strategy. It represents humanity's attempt to tame the forces of the universe for peaceful use. The dream of fusion began as science fiction. Now, it's fast becoming science fact. As we reach the end of this first section, one thing is clear. Fusion energy is closer than ever, but challenges remain. We are standing on the threshold of a new era in energy. Whether we cross it depends on our determination, investment, and cooperation. The fusion story is still being written, but its next chapter could change everything. The next phase of the fusion journey focuses on solving the remaining barriers between research and real-world deployment. To transform fusion from a scientific success into a commercial power source, consistency is key. A single successful experiment cannot power cities. It must be sustained, repeated, and scalable. Achieving net energy gain is just the beginning. The ability to maintain that gain over extended periods is the true milestone the industry now seeks. Long-pulse fusion reactions lasting from seconds to minutes must evolve into continuous operations. This shift requires not just plasma control but innovations across materials science, energy capture, and engineering integration. A significant barrier lies in the development of materials that can survive in a fusion reactor's core. These materials must endure temperatures exceeding 100 million degrees Celsius and neutron radiation that can weaken atomic structures. Conventional reactor materials degrade too quickly under these conditions. To solve this, scientists are developing advanced tungsten alloys and ceramic composites. These new materials resist erosion and retain strength under intense thermal and radiation stress. Another innovation involves liquid metal walls, which could absorb heat and radiation while self-repairing damage. Such advancements are critical for building reactors that can last for decades, not months. Then there's the challenge of breeding tritium, a rare and radioactive isotope of hydrogen. Tritium must be produced inside the reactor itself using lithium blankets that capture escaping neutrons. This complex fuel cycle must be efficient and safe to operate. A tritium supply chain is not yet established at industrial scale. Overcoming this will require coordinated global infrastructure and regulation. Beyond materials and fuel, there is the issue of power conversion. The energy produced by fusion reactions is primarily in the form of high-energy neutrons and heat. That heat must be captured and turned into electricity using turbines or other systems. Current steam turbine technology is well understood, but integrating it with a fusion environment poses challenges. High heat fluxes and fluctuating output require dynamic, adaptive thermal systems.
New methods such as direct conversion, where plasma energy is turned into electricity without steam, are also being researched.
These promise higher efficiency but are still in the experimental stage. All these components must be brought together in a functional, economically viable power plant. A commercial fusion reactor must be safe, efficient, reliable, and cost-competitive. Building and maintaining such a system at scale is the holy grail of fusion development. Equally important is the regulatory framework that will govern future fusion plants. Existing nuclear regulations are tailored to fission, not fusion. Fusion presents different risks and requires a new regulatory approach. Many experts argue that fusion should not be regulated like traditional nuclear energy.
It does not carry the same meltdown or long-term waste risks. Regulators around the world are working to establish fusion-specific safety and environmental standards. These will affect everything from reactor licensing to insurance and decommissioning. Countries like the United Kingdom have already passed fusion-friendly regulatory frameworks. This forward-looking governance is helping attract private investment and speed up innovation. International cooperation remains essential for addressing fusion's global scale. Projects like ITER are proof that fusion requires unity across borders. By pooling resources, knowledge, and talent, nations can share the burden and the benefits. Data from fusion experiments is now frequently published in open-access formats. This encourages faster iteration and cross-institutional learning. Standardized protocols and simulation frameworks are being adopted to ensure compatibility and transparency. This collaborative spirit mirrors the open scientific culture that led to the discovery of DNA and other transformative breakthroughs. But alongside cooperation, healthy competition is also driving progress. Fusion startups are racing to bring compact, modular reactors to market. They are not bound by bureaucratic structures and can pivot rapidly. Private companies often set more aggressive timelines than public institutions. This is leading to a faster feedback loop between theory and application. Governments are beginning to fund public-private partnerships to leverage the strengths of both worlds. The U.S. Department of Energy, for instance, is supporting fusion startups through milestone-based contracts. Such funding helps reduce risk for investors while ensuring scientific rigor. Venture capitalists are increasingly seeing fusion as a viable market. Funding rounds exceeding $100 million are no longer rare in the fusion space. With more money flowing in, startups can build prototypes faster and test new designs. The influx of talent from aerospace, software, and finance is bringing new perspectives. Engineers accustomed to building rockets and artificial intelligence systems are now solving plasma problems. Cross-disciplinary thinking is proving invaluable in a field as complex as fusion. Education systems are also adapting to meet the growing demand for fusion expertise. Universities are launching dedicated fusion engineering programs. Research centers are forming alliances with industry to offer hands-on experience. This workforce development is critical for building the supply chain behind future fusion infrastructure. Fusion energy will need welders, programmers, technicians, and systems integrators. Creating a fusion economy means preparing not just machines, but people. Public perception will also play a role in fusion's adoption. Unlike traditional nuclear power, fusion has not been associated with major accidents. It does not suffer from the same public distrust. Still, communicating fusion's benefits clearly and honestly is vital. People must understand that fusion is not a silver bullet, but a powerful tool in a diverse energy portfolio. Fusion's integration into the global energy mix must be strategic. It will likely complement renewables like solar and wind rather than replace them. Fusion offers a stable, dispatchable power source that can balance intermittent renewables. This synergy can create a cleaner, more resilient grid. Fusion could power regions where solar and wind are less viable. It could enable energy independence for countries currently reliant on fossil fuel imports. Over time, it may drive down electricity prices and reduce geopolitical tensions. The implications extend beyond Earth as well.
Space agencies are already researching fusion-powered propulsion. The ability to generate high thrust with minimal fuel mass is ideal for long-distance missions. Fusion could open the door to permanent bases on the Moon or Mars. Such systems would require smaller reactors and advanced power regulation. Breakthroughs in terrestrial fusion could quickly translate to space applications.
This dual-purpose nature makes fusion even more attractive. As we look to the future, fusion's role in climate policy will become clearer. It could provide the firm power backbone of a decarbonized energy system. Climate models show that meeting. Global warming targets without fusion will be extremely difficult. By mid-century, global energy demand is expected to double. Fusion could meet that demand without increasing emissions. It offers a path to energy abundance that does not come at the planet's expense. Abundant energy can drive innovation in other sectors, from water purification to advanced manufacturing. It can reduce poverty by lowering the cost of electricity and increasing access. It can improve public health by replacing polluting power sources. It can stabilize economies and ecosystems alike. But these benefits are not guaranteed. They depend on sustained investment, smart policy, and scientific breakthroughs. We must continue to fund basic research while also pushing for commercialization. We must train the next generation of fusion engineers and scientists. We must build international alliances that transcend political divides. We must align public enthusiasm with realistic expectations. Fusion will not arrive overnight, but with steady progress, it will arrive. And when it does, it could mark one of the greatest technological achievements in human history. The ability to recreate the power of the stars on Earth would be a triumph of science, cooperation, and vision. It would mean we have solved one of the most difficult engineering problems ever attempted. It would redefine what is possible for future generations. Fusion power is no longer science fiction. It is becoming science fact, one breakthrough at a time. The dream of limitless clean energy is beginning to solidify. It is no longer a question of if, but when. And as that day approaches, the world must be ready. The dawn of fusion power is not the end of the energy story, it's a new beginning. It invites us to think bigger, plan smarter, and act bolder. It demands international trust and long-term commitment. and it promises to light the way to a future powered not by scarcity and pollution, but by science and sunlight. Let us not wait for that future to arrive. Let us build it, one atom, one experiment, one generation at a time. Because the stars have waited long enough. Now it's our turn to shine.